today we will see some examples of group. Now the first example is let Z be the set of all integers. Okay, with respect to the binary operation addition. Okay, here let A and B be two elements in Z. Then obviously A plus B belongs to Z. So this shows that Z is closed under addition. Clear? And this is the first point of group. Now the second thing is addition is associative on the set R. We know that addition is associative on the set R, that is set of all real numbers, and Z being a subset of R, so addition, that is implies addition is associative on Z, and this is the second property of group. This is the first property. Now the third is 0 belongs to Z and 0 plus A equals to A plus 0, that is equals to A for all A belongs to Z. So therefore here 0 is the identity element of Z. Now the property 4, we know that addition now let A belongs to Z. Obviously then minus A, we can say that minus A in Z. That means minus A plus A, that is equals to 0, that is equals to A plus of minus A. So from here we can say that minus A is the inverse of A. So from these four properties we can say that Z, the set of all integers with respect to addition, creates a group. Okay. Now since addition is commutative on R, and since Z is subset of R, so we can say that addition is commutative on Z. Therefore, from these point, we can say that Z plus is a commutative group. Okay, so from these relations, similarly we can easily prove that Q, the set of rational numbers with respect to addition, the set of all real numbers R with respect to addition, the set of all complex numbers with respect to addition, all are commutative group. Okay, commutative groups. Now here we take the binary operation multiplication. Okay, multiplication on Z, the set of all integers. Then what happened? Is Z dot group? Answer is no. Answer is no. Why? Now Z dot is a commutative monoid, because one is the identity element, of Z with respect to multiplication. But the inverse of no element other than 1 and -1 in Z exist. Okay, so if there is no inverse element, so we cannot say Z dot is a group. That means Z with respect to multiplication is not a group. And similarly, we can easily prove that set of rational numbers with respect to dot is also not a group, because here 1 being the identity element, okay, but the inverse of 0 does not exist in Q. Okay, so it is not a group. Similarly, we can easily prove that set of all real numbers with respect to multiplication, set of all complex numbers with respect to multiplication are not groups. Okay, now here we take the set of all natural numbers. Okay, that is n equals to 1, 2, 3 up to ... This is the set of all natural numbers. Is n with respect to binary operation multiplication, n is n dot a group? Answer is no. Why? Because here the first property, suppose A and B belongs to n. Okay, A and B be two elements in n. Then A dot B obviously belongs to n. That means it shows that closure property satisfies on n with respect to multiplication. Okay. Second thing is, if now let A, B, C are elements of n, then A dot B dot C equals to A dot B dot C on n. So dot is associative. Okay, dot is associative, and that is closed. Dot is closed. And the third is, one is the one belongs to n. Okay, one belongs to n, this one, and any element A in we take any element A in n, then one dot A equals to A dot 1 equals to A for all A in n. Okay, that means 1 is the identity element in n, but inverse of no element other than 1 in n exists in n. Suppose 2 belongs to n, its inverse is half. Half does not belong to n. So we can from here we can say that the inverse of no element other than 1 in n exists in capital N. So we can from here we can say that the set of natural numbers n with respect to dot is not a group. Okay, but here belongs to the identity element. So from here we can say that n dot is monoid. Okay, and suppose that AB belong to n, then A dot B equals to B dot A for all AB in n. So this property shows that n dot is a commutative monoid. Clear?